You might have seen functions such as 4x to the 4 and been able to differentiate them pretty easily. This would have just been a simple power rule where you bring the 4 down and then minus it by 1. So if we took the derivative, that would be 16x to the 3. So that's perfectly valid in this scenario, but what if you are given 4x plus 1 to the 4? Are you able to still use the power rule? So it turns out that this is not the case, and that is because this is a composite function. It is a polynomial within a polynomial, and we actually have a special rule for that. So you'll see this definition over here. If we have the derivative of f of g of x, so the composite function of f and g, we actually take the derivative of the inside of the function, the g of x, and multiply that by the derivative of the outside of the function, or what's wrapped around g of x. So let's do that real quickly. So I'll get rid of this. So if we wanted to take the derivative of our original equation, I'll just rewrite it here for simplicity and a little bit bigger. This is actually saying we'll want to differentiate the inside of the function. So let me take this derivative. So that is of that 4x plus 1 multiplied by the derivative of the outside of the function. And I'm actually going to use u to represent the g of x right here. So I'm just going to replace the 4x plus 1 with a u. And you can write that somewhere. You can say u equals 4x plus 1. Just to make it clear that we are differentiating the outside of the function, or the f of x, and not the inside. And if that's kind of confusing, you can just view this as two functions. The first function, g of x, being the 4x plus 1, and the outside function f being the variable g of x to the 4. So that's why I wrote it as u to the 4. So the first derivative of this, so using the summation rule, we can take each derivative separately. The derivative of 4x is just 4. And then the derivative of 1 is 0 here, multiplied by the derivative of u to the 4, which is 4u to the 3. So we just treat it like a normal variable now. So that equals, we're going to multiply 4 by 4. That becomes 16. And I'm going to replace the u as 4x plus 1. And put the 3. And that's actually our final answer. So it's not too difficult. You just have to recognize what is actually going on and not just treat this like a variable. If we treated this just like the power rule, this would have been equal to, and I'm going to make this clearly not equal to 4x plus 1 to the 3. So that's not what we want, and if you wrote that, you would probably get a 0. Okay, let's go to a slightly more difficult example. Our next example is going to be f of x equals x times the natural logarithm, or ln, of x plus 1. So let's take the derivative. So right away you'll notice that it is two functions multiplied by each other, and so we're going to actually need the product rule for this. So let me just put equals here. So we'll take the derivative of our first equation, which is x, which is just 1, multiplied by just g of x. We don't do anything to the ln right now. So I'm going to write that. Plus, now we leave the x on its own. And we're going to need to take the derivative of our g of x, which in this case is ln of x plus 1. So if you've never seen the derivative of ln before, let me just write it here. So d by dx, let me write that a little bit better, of ln x equals 1 over x. And this is actually using the chain rule. So we then multiply this by the x itself, similar to the chain rule before. So let's do that real quick. So the derivative of the inside of the chain rule is going to be x plus 1, because this is a function, a polynomial within our logarithm. So this is a function within a function, and so we have to use the chain rule. So the derivative of x plus 1, the derivative of our x is 1 plus The derivative of a 1 is 0. And I'm taking the derivative of both individually because remember the summation rule. So maybe to make this a little bit easier, we take the derivative of g of x. Then we're going to multiply this by our 1 over x, where the x in this case is our entire g of x. So that is x plus 1. Oh, x plus 1. So writing that all out, 1 times ln of x plus 1 is just ln of x plus 1, plus that x is going to multiply into the 1. So then it's just going to be this x, and then of course the 0 makes it the next term 0. X plus 1. Oh, and I forgot the 1 there. And that's actually our final answer. Okay, so for our next example, we are given the function of e to the x squared plus sine to the x squared. Now, at first, this may seem pretty complicated, but just need to break it down step by step. So we see that we actually have a function, e to the g of x, where our g of x is this term here. So let's find the derivative. So f prime of x equals. So remember, we will take the derivative of our g of x term first, and you'll notice that there's actually a sine x squared here. So we're actually going to need to use the chain rule on the sine term when we differentiate it in the chain rule. So we're going to need to use two chain rules. So I'm just going to write this down step by step just to ensure we do not miss anything. So we'll need to take the derivative of this x squared sine x squared times, and then the derivative, so this g of x is going to be replaced by u. So that is, remember, e to the x, and let me actually write this here. The derivative of e to the x equals itself. It's unchanged. And so when this g of x term is replaced by that u, and we're only doing the outside function is e to the g of x, which will just be itself. So we're just going to, and I'm just going to write, just because I'm running out of room here, that is our g of x term. I'll put that back in. I just have all this text here. So let's take the derivative of this. So the derivative of x squared is just 2x. That's just the power rule. Then we're going to actually take the derivative of sine of x squared. So I'm going to put these brackets. So that x squared is going to come out. Again, if you're ever confused on what to do, you have to find the two functions. The first function, g of x, is going to be that x squared, and then you're going to want to have that as sine of g of x, because all you're trying to do is convert this into a form you can actually differentiate. You're trying to find that outside function. So then that is going to be the derivative, again, of x squared, and this is this sines x squared, not the x squared from before, times, and then the derivative of sine is cos, and I'm just going to put that equation back in, times e to the g of x. So let's write that again. So that will be 2x, and remember, I should have been clear with these brackets. This is all going to be multiplied by our e of g of x. So that is 2x plus the derivative of x squared, again, 2x cos x squared, all multiplied by e of x squared plus sine x squared. And that is our final equation. And you can, of course, multiply the e of x to each of our terms, but this is the final answer. Okay, so for our final example, we're actually going to do two trigonometric functions, and you'll actually see here that I added the definitions of sine and cos here, and you'll notice here we actually have x over 1 plus x. This is going to need the use of the quotient rule, which I've also put here, and I put them all in boxes just to make that look nicer. So let's get right into it. So by now you should probably be picking up on the pattern that we are wanting to get these composite functions differentiated using the chain rule, and we're going to want to have it look like something we know. So once this sign becomes sine x or sine of u, it's really easy to differentiate it. So we're going to pull that square root of x outside. So I'm just going to write d by dx, and actually instead of writing the thing, I'm going to put x of 1/2. Again, I'm just making it to an easier form. These are the exact same, they mean the exact same thing. We can just see that it needs the power rule right away. And then we're going to want to differentiate that sine of u. Again, u just being that the square root of x. I'm just putting it as sine of u just so it looks like something we know. And then we're running out of a little bit of room here, but we're going to want to then differentiate this. And again, the exact same thing. So I'm going to write this d by dx, pulling out that x over 1 plus x times cos of u. And so let's differentiate this. So I'm just going to write this equal sign over here. So x to the 1/2, you bring the 1/2 down, and this becomes x to the minus 1/2. And again, this is not the product rule. We are just multiplying the chain rule, or we are just multiplying it by itself. So this is cos of u, which becomes, when we substitute the u in, cos of the square root of x. Just make sure about that when you are writing it like this. This might not be the best notation. If you forget, this is not the product rule. This is the intermediate step of the chain rule. I'm just writing down the steps. Plus the quotient rule. So the derivative of x is just 1 multiplied. We keep the 1 plus x on its own. Minus, we then leave the x on its own, and we differentiate 1 plus x, which is 0 plus 1, all over 1 plus x squared. Then this is multiplied by cos of u, which is sine, and then plugging in the u, it is negative sine, because the derivative of cos is negative sine of x over 1 plus x. And let me write that a little bit nicer. So this cos of x is up here. And then minus 1 over half, this can be rewritten as the square root of x underneath plus. Just simplifying this, this becomes 1 times 1 is 1, 1 plus x minus x times 0, 0 minus x. And then we can actually see this plus x and minus x will cancel. So I'm just going to remove them and just leave this as 1, which this sign will be. So this will be 1 over 1 plus x squared it's not 1. Let me write that. 1 plus x squared times negative sine of x over 1 plus x. And that is our final equation here. Let me just do this. So we did have to use the chain rule twice and some trigonometric ratios, trigonometric differentials, but it's a pretty straightforward process. All you do is you find your composite functions and then multiply it by the derivative of the outer function. So that's about it. If it helped, definitely leave a like and comment if you have any questions, and then subscribe as well.